Hi, this is Roger from Kanka Labs, and today, as promised, part 3 of our video series about how to suppress oscillations. This time it's about digital logic, and we'll take a closer look at how to suppress unwanted oscillation in digital high-speed logics. Well, you will know the common practice just to place a 100 nanofarad bypass capacitor at the voltage supply terminals, but we'll take a closer look at why this is necessary and that even modern components, modern ultra-low ESR bypass capacitors can be worse than the old ones with worse values, with a worse ESR. So now let's just start and take a look at how a CMOS output stage is looking. Well, you have your traditional pair of an N-channel and a P-channel MOSFET, which look like, or are drawn like this. Here we have our P-channel FET, and down below we have our N-channel FET. Where the body diode, the gate substrate, and the source are drawn together. They go to ground, and now the outputs of the two are connected as well as the inputs. And now the operation is simple. Well, it looks a bit more complicated than it really is. You have your P-channel FET connected to VCC and your N-channel FET connected to ground. The output, the drains are drawn together. And now if we put 0 volts at the two gates, then your P-channel MOSFET will turn on, and connect the output with your supply voltage. And when you put 5 volts or VCC to the gates, then your N-channel MOSFET turns on while the P-channel is turned off, and it connects the output to ground. And so this is the basic circuit for an unbuffered inverter in CMOS logic, but we can look upon this as much easier. It's simply a switch, a dual pole single throw switch, which connects the output between VCC and ground, or sometimes it's called VDD and VSS for drain voltage and source voltage in CMOS logic. So, but there is still one important parasitic element, and that's the drain source resistance. And they are made, the two transistors in a CMOS output stage, they are made as equal as possible, so we can think of them as having the same drain source on resistance. And here is your output of your CMOS output stage. So we don't need to know more about this, because we're not interested in the other parasitic elements of our CMOS output stage. It's absolutely sufficient to know that the output is simply switched via the drain source on resistance between VCC and ground, depending if it's a 1 or a logic 0. And now, but what we do have to consider is the next input that this output is connected to. And let's make another drawing. So we have our simplified double pole single throw switch. With our resistance. That is basically the output stage. And now comes the input of your next logic. And what does that consist of? We leave out the ESD protection diodes, etc. But every input has a parasitic capacitance. And that is always in the range of around 5 picofarads. If you compare the different logic series available in CMOS, you will always find this is very near to 5 picofarad, might be 3 sometimes, or in standard CMOS logic a little bit higher, but we take as an average 5 picofarad. And now what's the RDS on? Well, that depends on your logic family. It's in the range of 1 kilo ohm for your standard CMOS series, the one that the oldest, the CMOS series, that is operating between 3 and 15 or 3 and 18 volts. It's in the range of 100 ohms for the HC CMOS or HCT, it doesn't make any difference. And for ultra high speed logic like AC and ACT, it's in the range of 10 ohms. And you can already guess the reason why. When the output switches from VCC to ground or the other way around, first of all, the capacitor has to be charged, and it has to be charged that quickly that first of all we don't have a slow rise time, and between charging and discharging the time must be as short as possible to reach the highest speeds. And you know, this sequence here is also a sequence of speed. CMOS, depending on which kind of logic gates you buy and from which company. For example, the NXP series is the fastest CMOS series, the HEF series. There you have speeds in the range 1 megahertz up to around 5 megahertz. Some gates even go to 10 megahertz around. In HC CMOS, you're much faster, around a factor of 10, depending on the type of IC you get. It's between 10 and, I don't know if it goes up to 50 megahertz, but it could be that some simple logic gates go even to 50 megahertz. And H CMOS is still faster. It goes in the extreme up to 100 megahertz. And then it becomes clear, for example, in 100 megahertz, a transition from 0 to 1 and back again must be less than 20 nanoseconds. So you have 10 nanoseconds between one transition from low to high, and that must be that must not be worsened by your RC combination, because it just takes time to charge your parallel capacitor. And you know from a simple RC circuit that the lower the resistor is, if you have a fixed capacitance, the faster you can charge this up. And of course, this also gives a little current spike when this capacitor is charged, when it goes from 0 to 1, or discharged when the output goes from 1 to 0. You get a little current spike at the beginning and at the end of each transition. And we'll see in our simulation how large this current spike can be, and what it has to do with suppressing oscillations here at VCC. Because if you ever have measured with an oscilloscope a digital logic IC, and even you did it properly with a short connection to ground, with a little spring at your oscilloscope that directly goes to the ground at the IC, and you took a high-speed oscilloscope and a high-speed probe, you will see here that you always get some ringing here at VCC. And the question is, where does this ringing come from, and how can we suppress it? And the first fact you have to, or what you will guess, is that of course you have the copper resistance from your power supply, your regulated 5 volt or 3.3 volt or whatever, that you have that the copper resistance is the culprit here. No, look here, we have resistance in the range between 10 ohms and 1 kilo ohms, and you really have to make the worst PCB layout to get this as high as 0.1 ohms. So the copper resistance never plays any role, but each PCB trace is always an inductor, and that's where the problems come from. Depending on how you lay out your PCB, if you have a ground plane or not, and how what's the width of your PCB trace and what's the length, the inductance can be between 1 and 10 nanohenries per centimeter. And you might think, well, a few nanohenries, what can do that? Well, we'll look in the simulation what a few nanohenries of inductance can do to your supply voltage, and in the end to your signal shape, and even to malfunctioning of your gates. So let's again go over to LTSpice and take a look. So here we have our simplified CMOS output stage, and with our pair of P-channel and N-channel MOSFETs, I've chosen just two available in the LTSpice libraries available logic level PNP and P-channel and N-channel MOSFETs. So the simulation result depends heavily on which transistors you choose. We have our 100 ohm RDS on output resistance. We could also, in theory, put this directly here in the model of the MOSFET, but to make it more clear and to be able to measure the current here through the output resistance, we'll just make it external, and we have the input capacitance of our next gate, and we put a square wave on the input on the gates of our PN channel CMOS pair. And again, this time I did not make the error just to leave the rise and fall time at the default 0, but we take 5 nanoseconds rise and fall time, which is quite typical for HCMOS ICs. We take an on time of 20 nanoseconds. That is a 25 megahertz signal, because the period time then becomes, if it's symmetrical, is 40 nanoseconds. So this is a simple signal, but already at quite a high switching frequency. And we have our 5 volt voltage supply, and I've already added the PCB trace inductance from our ideal voltage source, and that would be a regulated 5 volt power supply within 7805 or whatever. But first of all, let's set the inductance so low that it is nearly negligible, as 0.1 nanohenries, or what is it, 100 picohenries. But I've already put in the series resistance. That's the copper resistance of your PCB trace, as 10 milliohms, which is quite typical if you don't have a meter long of PCB trace, but only a few centimeters. And already added what you also always have, the parallel capacitance, because of course your PCB trace has a capacitance down to ground, or in this case it's parallel to the inductor. But so this is not a pure inductor now, it's a more or less it's a resistor with negligible inductance for our first simulation, and basically only the copper resistance. And so what we want to know is, first of all, how does our more or less ideal square wave at the input of our CMOS pair look at the output, or better said, at the next input of the next gate? What is the current through for charging here? And this current spikes, of course, transfer to current spikes here on the supply lines. We take an ideal ground and we only look at what happens at VCC, at the positive supply voltage. How do you get a perfect ground? Well, if you're using a ground plane in your PCB, that's the next best thing to an ideal ground. Otherwise, if you have extra PCB traces for your ground, you would have also to insert an inductor here to ground, which makes things still worse. But let's not get too complicated. Let's start our simulation. And we said we wanted to know, how does the voltage look here? Okay, this is still a reasonably, how do you say, sharp or sharply rising and falling square wave. So the next input will have no problem with dealing with the square wave. We see a little bit of overshoot here and undershoot here. That comes from, part of it comes from the parasitic elements here in the transistors, but mainly it's already here from the inductance here. Now let's see what the current through our output resistor is, and here you can see the current spikes when charging and discharging. It goes, that's already surprisingly high. It's 10 milliamps for one gate, just one gate. And if you have an IC with 4 or 8 outputs, this of course multiplies if all are switching at the same time. So with HCMOS you already have surprisingly high switching currents. At standard traditional CMOS, this is 10 times lower, and at the problematic AC ultrafast logic, this problem is notoriously known as being quite difficult to handle with. And let's see what our supply voltage. Now, of course, here we have a perfect 5 volt, and how does it look here at the VCC input of our CMOS IC or CMOS inverter? Well, it's nearly constant because we choose the inductance so low that the wiggle you see here from the charging and discharging is nearly unrecognizable. But now let's change this inductance to a more typical value, and let's really do a very long and bad designed copper trace of 100 nanohenry. You can get this already with 10 centimeters of PCB trace from your regulated voltage supply to your IC, and 10 centimeters is not uncommon in PCBs, especially if you're not using SMD but using through-hole parts, which are 4 times larger or more than 4 times, depending on which. And look what we get now. Unbelievable. This 100 nanofarad without a bypass capacitor. Look what our supply voltage is doing. It goes here. It wreaks havoc. Unbelievable. The output shapes are unrecognizable. So that is the reason why you absolutely have to insert a bypass capacitor. If you didn't do it now, we even get overshoots up to 10 volts, which could potentially destroy your IC if there's enough energy in this voltage spike. Unbelievable. So now the simple remedy for this is, of course, inserting a bypass capacitor of traditionally your 100 nanofarads with every IC, and perhaps every 4th or 5th IC in a row you put a tantalum or aluminium electrolytic of, let's say, 10 microfarads, but we'll only take a look at this directly with the shortest possible leads. Why the shortest possible leads? Just to avoid, again, an additional inductance. And that's also the reason why SMDs are better for high speed than through-hole, just because the traces are much shorter. So we'll give this a value of 100 nanofarads, your traditional bypass capacitor, and see what we get. Oh, we have nearly restored our original shape of our waveforms. The power supply, the VCC directly at the IC, is nearly constant at 5 volts. You can't see any wiggle. Our output of our CMOS pair, or better, the input of the next stage, again has this little overshoot, but it's no problem. We have relatively sharp rising and falling edges, and we still have back our peak charge and discharge currents of plus minus 12 milliamps. So if we just take the wrong component and we take 100 picofarad, just a factor of 1000 too low, then we again have our problem. So 100 nanofarad, there is a reason why this is your standard value for a bypass capacitor for each single logic IC. And now there still can develop a problem. Let's go back to 100 nanofarad, and what we have neglected until now, that is the ESR, the equivalent series resistance of our capacitor, and the equivalent series inductance. So let's first of all take a look at what are the parasitic elements of a capacitor. Here we have the main element, the capacitor. We leave out the insulation or leakage resistance because it is of absolutely no importance in bypass applications. So what remains is the equivalent series resistance and the equivalent series inductance, ESR and ESL. Now you might recognize these three elements in series are nothing else but a series resonant circuit, and this is verified if we take a look at a how the impedance runs on a real-world capacitor. Here, at first I've taken from the datasheet of, I think it's VIMA, a 100 nanofarad plastic film capacitor, how the impedance runs with the frequency. And you can see here there's a whole range of different values, but you can see they all look like a V shape, the shape of the letter V, and this is typical for a series resonant circuit. The impedance drops linearly here in this double logarithmic graph up to a minimum point, and the minimum impedance is direct. You can directly read it off. It's the ESR, and for our 100 nanofarad capacitor this gives around 150 milliohms, and at the point where the minimum is, this is the resonant frequency of our series resonant circuit, in this case 7 megahertz. And from that, together with the value of your capacitance, you can simply calculate with the formula for the resonant frequency what the corresponding inductance is, and this gives the ESL. So from this graph you can directly read or calculate all values, also the Q factor, the dissipation factor if you want to. But we only are interested now in the ESR and ESL, and let's put these values of a plastic film capacitor, which is, as you might know, is not recommended as bypass capacitor for high-speed digital logic. Let's put these values, 150 milliohms ESR and 5 nanohenries ESL, into our component, into the parasitic values for our bypass capacitor, and see what happens. Now let's probe first of all here at this point the supply voltage, and surprise, surprise, we get here our oscillation, and the maximum and minimum values are already well above the tolerance that is allowed, which is usually only 5% for digital logic. So the maximum excursion goes to 6.3 volts, and the minimum voltage is around 4.1, 4.2 volts. And let's see how this translates here to the point where the input stage of our next digital logic gate would be. And the shape is still okay. There's a little wiggle here in the high state, but it's still within limits. So although plastic film capacitors are not recommended, and you can see now why, they would still probably work even here with a high-speed CMOS gate driven at 25 megahertz, but it's already coming to its limits. And let's see, as a last thing, the current spikes through our output resistor, or the RDS on of our MOSFET CMOS output stage. And there you also can see these little excursions here, but the blue line, that's what's important, what really arrives at the next input stage, and it's still okay. Now let's compare this with what we get with a modern MLCC, a multi-layer ceramic capacitor of the same capacitance, 100 nanofarad. And you already can see the resonant frequency is much higher at around 25 megahertz. The ESR is much better, 3 times lower at 50 milliohms. And the ESL that I've calculated from these values it was exactly 0.4 nanohenry, so more than a factor of 10 better than a plastic film capacitor. And let's put these values into our capacitor. What did we have? 50 milliohms ESR and 0.4. I've rounded this up to 0.5, but let's take the exact value, 0.4 nanohenries, and see what we get. And you can see that it's much better. The supply voltage, there's nearly no drop or no ringing. It's so low that it will be even difficult to see on your scope. And the here the waveform itself is nearly unaltered due to this very small ringing here. So it's nearly perfect. And so there you could see the reason why modern MLCC capacitors are a factor of 10 better than using plastic film capacitors as bypass capacitors. But we haven't answered the question, does it make sense to put a series resistor here to dampen out any unwanted oscillations? Now, here in this example, we don't have any oscillations, but there is really an application where it makes sense to add a series resistor here, but that will be discussed in the next and probably final episode. So here we've only verified you have to use a bypass capacitor, you have to choose the right value. Standard is 100 nanofarad, and better use modern ceramic capacitors than plastic film capacitors. So that was it for today. Thanks for watching. Until next time, bye from Roger, bye from Kanka Labs.